Okay, troops. Just to go through the procedure. Oops, our tablet's off. Yeah, just a draft kind of form like you would write out in the pre-lab. What we're going to do is we got the air track, and we consider these two masses. So this would be a sled. There's a pulley, and this will be a hanger. And the hanger is, I assume, going to be this hook-shaped thing, and it has a disc on the bottom. And then we're going to have these series of weights with the slot in them, and you slide them on there. So I think something like we'll have 5 of these weights, and maybe they'll be 50 grams apiece. I don't know, but we'll have to see what we get when we get there. So constant force, variable mass. So that means that we're going to put some mass on the hanger, little m, and that's going to stay constant. And then we're going to, for each, say we take four runs, and each run will have a different capital M. So let's say we put M here, little m, let's say for the sake of argument, is 1 weight. And then we'll do, so you do 4 of the runs, where you could imagine having 1, 2, 3, 4 weights onto the sled. And then a run will be, we'll be taking, we have the gates, remember? So there'll be S and T. So we'll be writing down the position. Well, yeah, this S and T, we can create a data table right off the bat of the S positions, because those will always stay the same, right? So then, for each run, we write down little m. So this case, don't forget there's a mass of the hanger. So in this case, little m is always going to be 1 weight plus mass of the hanger. We don't know these numbers at the moment. And then, so each run will have that, and then each run will have a different value for capital N. So we're going to be taking, let's just assume they're 10, 20, 30, 40, etc. And then T1, well, let's see, we call this 0, T1, T2, T3. And then for each, so there's going to be 4 of these tables, S and T data, with a little m and a capital M. And then we'll use our then we'll determine A, acceleration for each run, using the fit mechanism that using the lab 4 technique. But you see, this could get pretty tedious, but since we already have all that, we just have to copy paste a whole bunch of these. So we're going to have, for the part 1, we're going to have 4 of these graphs. We won't need this part here. I'm going to set that up for you. So then we would say here, like in this case, so this is this is constant mass, so let's not, so this is going to be constant force. So we're going to say little m equals whatever number of grams. Let's say 50. Let's say the hanger, I don't remember what the hanger weighs. Let's say it's 90 tab, and it's grams. And then capital M, will, oh, when do that equal sign? Oh, that's not what I wanted. Capital M. And then this number will be different each time. And let's say, well, and we have to weigh the we have to get the mass of the sled too, don't forget. I forgot that. I'll put it over there. So let's say this is 150 for this particular run, and grams. And then we'll get, this is the same each time, and then we'll get 4 different runs, so we'll be able to just copy paste. Well, actually, I suppose we copy paste this mess just twice. We keep this, we just rename that. I'll go through that in another video. Right now, I just want to get the general roughing out. So then, I guess I could have left myself some more room here. So we're going to determine A for each run. Nope. Don't want to erase the formula. I'll pause this for a moment. So I remind you that capital M is going to equal the number of weights and times whatever they are. Let's say, for example, they're 50 grams plus the mass of the sled. And then little m is going to equal the number of weights times, say, for example, 50 grams, whatever they are, plus the mass of the hanger. So, and then we'll get, for each of the 4 runs, we're going to get an acceleration. So then we're going to have, say, acceleration 1. That's going to have capital M1, but the same little m. A2. So we're going to then create a separate table. And A3, capital M3, little m, capital A4, capital M4, little m. So then we're going to create a graph. Well, we're going to extend this table too. Let's keep it going then. So what we need is a column that is little m. So let's say this is A, capital M, little m plus big M. And let's just get this out of the way. All right, then we need 1 over m plus m, capital M plus m, and we need mg. So this is what we have to create that's new. Although we could just go straight into 1 over m plus m if we wanted to. So then we're going to create a graph. And we're going to put A on the y-axis. And what's on the x-axis is, force. Oops. We don't want that. We want 1 over m plus m. So this is something new. And we'll get to it. The reason we're doing this is because it comes from the days of having to use paper and pencil, and it was just always easier to do a straight line fit with paper and pencil. So then we'll have our pairs of these things, because there's going to be the 4 data points. So I don't even remember if it's going to be positive or negative, but there'll be 4 data points. And the slope of this thing should equal mg, which is the force. And so that's the mass, little m times the acceleration of gravity. So I saw that I made another mistake. So you see that this is y equals mx. This is our x. That's our x coordinate. That's our y coordinate. This is our slope. And then, so we're going to get the force, basically, which is going, we can calculate in newtons, if you like. So you can always, we can say that's F because weight is a force. And then, so we'll determine what is the slope there. It should be a constant. And it should equal, to the best of our ability, the mass times 9.8 meters per second squared. But for now, all we need to do is rough out that we're going to produce this data table. We're going to determine the A for each run, and then we're going to plot these two. And what's new is using 1 over m plus m. And we'll determine some kind of one plus or minus mg. And we'll probably just go and do that standard deviation of the residuals once again. Okay, so now we're going to do constant mass. So what that means is that we're going to maintain capital M plus little m. We're going to maintain it as a constant. So that means is that we'll say we'll have our 5 weights. And we'll do again 4 runs, but what that'll mean is that there'll be let's say little m, big M. So let's get this out of the way. So once again, we'll do 4 runs. We have 5 weights, right? So what we're going to do is we're going to say that we're going to put 1 weight on here and 4 weights here, then 2 and 3, then 3 and 2, and then 1 and 4. So that's 1, 2, 3, 4. And something doesn't seem right here. 1 and 4, 2 and 2, and 3, 2, and this is supposed to be 1, and that's supposed to be 4. Okay, so notice how capital M plus M is going to be a constant. Now, don't forget that we have to add in plus weight of the hanger and weight of the sled. So we need to know what is the mass of the sled and what's the mass of the hanger, but that stays constant throughout. Then again, each one of those runs, we're going to get the S and T data, and then we're going to get A again, 4 A's again. And then what we do now is, this is our Y, this is our slope, I believe, yeah. And well, let's make sure. I might have done this wrong. You know, I've never liked when they tell us that we have to put, they want to put acceleration as the dependent variable, and I never like that, because really A is, since it's something we measure, it should be the what's so-called dependent. So we vary we vary the force, and then we measure A. So that's the independent, dependent. So dependent is the thing we vary force, and then we measure A. I might have said it a little bit wrong there. So I don't like this. I like it better like this. So it looks exactly like the same equation, but what's different is now that when we plot our points, we should expect greater force, or should expect a positive slope. And when we do the fit, well, it's only 4 points. I drew a bunch. We should get a slope that's equal to the 1 over m plus m. We can compare it to the these numbers here, and it should, first of all, it should be linear, and meaning it's a straight line, and we'll see how much error we get out of it. We'll come up with some reasonable way to determine the error. And then this one here, right, we're varying the mass, but because it's a inverse relationship, we put 1 over for the x-axis. And then, so then let's see, that's good, because then that means that if we make this m plus m bigger, that means that then, right, so this will be a smaller number, and then a will be smaller at the same time. So that'll be positive slope if Newton's law is correct. And obviously, we know if f equals ma is pretty straightforward. There's force, there's a. So this should also equal a straight line. Now, something is bugging me. Because, yeah, a equals f over m. A equals f over m, excuse me. If Newton's law is true, that should be true. We vary force, and the slope should be inverse of this. And good. So notice the difference once again. In this case, the mass of the hanger, which is the accelerating force, is constant. And in this case, the sum of big M and little m is constant. All right, very good. That's enough for now.